All right, so we've got problem set 16 now. And I'm just noticing that this is a little bit blurry, so I'm really sorry if that's a little hard to read. But you'll notice I've kind of set it up a little bit differently this time. It's just because I wrote out all of the questions on paper and scanned them in this time, just because that was easiest for me. The next two problem sets will probably be the same, so just quick heads up there. And yeah, so we've got all these questions here. And I think that there is, I think it's on this homework. One of the questions is, has something to do with the probability of the distance of an electron from like atom or something along those lines. One of the questions in one of the homeworks is like that. It's either on this homework or on homework 17. I just want to say up front that I do not go over that question in any of these problem set videos because I was having a very difficult time figuring out how to rewrite that question in a way that would not be the exact question itself. And I'm not comfortable presenting that just because that could be, cheaty. And we don't want that here. So if you're having trouble with that, I'm sorry, but these problem sets do not cover it. But it should be the same concept as all the rest of them. It's just a little bit more difficult to work through and simplify just because there's so much going on with that one. But we'll go ahead and start with number 1 here. So f of x equals this right there, and we want to find the derivative of this function and then its critical numbers. Okay, so if f of x equals this, well, we know to take the derivative of this that we've got to use our product rule because we've got a product of two pieces that both have our variable in them. So remember, the product rule is the first term times the derivative of the second term plus the derivative of the first term times the second term. So we'll take that first term and just keep it as is. Remember that this is also the same as the cube root of x, just in case we need to use that later. Now times the derivative of this. This bit's just a little bit tricky because we have to use chain rule there. So I'm going to say our outside is, we'll call that n, and that's our outside is something to the power of 2/3. And if I derive that, it's going to be the derivative of the inside times the derivative of the outside. Okay. And then our inside is a 2x plus 10. And the derivative of that is just 2. So then what happens there is this is going to be 2, right? Times 2/3 times m to the negative 1/3. So I can actually just put that on the bottom of this fraction here to get rid of that negative. So now it's just 4 over 3 this. Let me just plug m back in. So it's going to be 4 over 3 2x plus 10 to the 1/3. Okay. Remember, this is just power rule. So I brought my 2/3 in front and then I subtracted 1. And 2/3 minus 1 is obviously just negative 1/3. So that's where that came from, in case anyone was lost there. Sorry. And so now I've got this first bit here. I've got my first term times the derivative of my second term. Now we add the derivative of my first term. So that's going to be derivative of this. Again, power rule, so just 1/3 in front. Now times x, subtract 1. And I could rewrite this like so. And I think I am going to write it like that over here. Okay. And then times that original thing. And since it is, well, no, I can do that in a minute. So I'm multiplied by our original second term there. And this is our derivative. Now we just kind of want to clean that up a little bit. So since it's multiplication, I'm just going to move it on to that fraction there. So it's going to be 4 that over I'm going to rewrite that as a cube root. And this also goes on top of that fraction. And that's another cube root. Actually, should also write that as a cube root, I suppose. Oh, this should be an x. Cube root of x. And no. Sorry, I'm actually going to keep them with those powers. I think that actually makes the most sense looking at it. Either way really works, but some ways are just a little bit easier to look at than others, in my opinion. Okay. So now, there's the tricky bit. We want to find a common denominator. Easiest way to do that is to just multiply them together, right? So multiply the denominators together. This multiplies with this multiplies with this, and then we can add them in that same numerator. So if I have, well, we'll go ahead and multiply that top bit first. So it's going to be 4x to 1/3 times 3x to the 2/3. Well, our coefficients just multiply together, so it's going to be 12. And then when we multiply two things with the same base, we just add the exponents. So it's going to be 1/3 plus 2/3, x to the 3/3, or just x to the power of 1, right? Or just x. So that turns into a 12x up there. So I'm going to write 12x. And then I'm going to multiply this with this. I'm going to erase this part real quick. And it's the same deal. So it's 2x plus 10 is our base there, to the power of 2/3, times 3 times 2x plus 10 to the 1/3. Remember, this is the only part that's to the 1/3. So this is a coefficient. These are our bases. So again, coefficients multiply together. So that just turns into a 3 times our base to the power of these added together. Again, 2/3 plus 1/3 is 3/3, or just 1. So I can just leave it like this. So it's going to be plus 3. And I'm going to go ahead and distribute that actually. So it's going to be not a 3, but a 6. 6x plus 30 all over whatever that common denominator is. So multiply the coefficients together, but then these parts are going to stay separate. So it's going to be 9, and then this here, and then this here. Okay, and now I can combine like terms there. So our derivative becomes this, and I am actually going to switch these terms around really quickly so that it looks like so. And now, I think that's as simplified as we can make it. We might be able to do more. Oh, actually, I see we can factor out a 3 from all of that. So I'm going to go ahead and do that because we like to simplify as much as possible. So factoring a 3 out of my 18 makes it a 6. 3 out of my 30 makes it a 10. 3 out of 9 makes it 3. And the rest is the same. So there's our derivative. And if we look at it, that's the exact same kind of terms they wanted over here. So we see that A is going to be our 6. B is going to be that 10. C is going to be 3. D is going to be 2/3, because that's right here. And then our E, oops, I left out that. Our E is going to be that 1/3 there. Okay, and now all that's left for this question is to find the critical numbers. I know the derivative was kind of a little tedious, but now that we know it, finding our critical numbers is an easy task because we just need to figure out when it equals 0. We'll notice that there shouldn't be anything out of the domain except for like x equals 0, because if x is 0, then this is 0, making the whole denominator 0. So we know x can't equal 0, but everything else, these are cube roots, so negative numbers are allowed in them, so our domain should just be everything but 0. So knowing when the actual derivative equals 0 only matters from the numerator, right? Because the denominator just doesn't change much. So yeah, so we want to know when 6x plus 10 equals 0. That's going to be 6x equals negative 10 divided by 6. X equals negative 10/6 or negative 5/3. And that looks to be our only critical point. The 0 is outside of our domain, but it is a point that we would want to look at how stuff moves around it. So we might consider 0 a critical number. I don't remember if our homework considers that a critical number or not, but I am going to write it for right now. And then we don't have another one. Because when we're looking at our intervals, right, when I'm going like negative infinity up to negative 5/3 and onwards, sometimes we want to see what's happening right around any asymptotes or holes that we have. So for example, if I have something that looks like it's doing this, it's a good idea to just be able to look at that with my intervals there. But that's all they ask from us for this, so we're going to go ahead and move on to question 2. Question 2 says if C of X is the cost of manufacturing X amount of a given product, and $4 is the price per unit, then the profit, P of X, is obtained is P of X equals 4X minus C of X. And all of that means, like, this makes sense, right? It means that the profit is the price times how much is sold minus the cost that it takes to produce. So let's take a look at this first question here. It says if the cost is some lowercase c times x, and that lowercase c is less than 4, is there a maximum profit? Well, if we're looking for a maximum, of course, we have to take the derivative of our profit function. So the derivative of that is a nice easy one. We just use our power rule and technically our sum difference rule. So the derivative of 4x is just 4. And the derivative of cx, well, c of x is going to be c because this is some constant coefficient. So it's just going to be this, right? And if c is less than 4, our derivative can never equal 0, which means that we don't have any critical points, right? Because if c is less than 4, that means that no matter how much I subtract, no matter what c is, if I'm subtracting it from 4, I'm not going to get 0 any point because it would have to be at least equal to 4 for that to happen. So that tells us that there is not a maximum profit. And yeah. Let's go ahead and take a look at B. Now they're saying if c of x is this equation instead of that, find the maximum profit. Okay. Well, first we have to find the derivative of this to plug it into our derivative equation, right? Because we know that the derivative of p of x is going to be 4 minus the derivative of that equation. So let's find the derivative of c of x. Well, first we've got chain rule. So I know that I've got the derivative of my outside, so I'm going to put that 2 in front of my inside times the derivative of my inside. Well, the derivative of my inside is just 1, so it actually does just get left like this. And then plus 15. The 15 goes away because it's a constant. So this is the derivative we've got there. And I'm going to go ahead and distribute that too. Okay. So now, derivative of p of x is minus 2, or just this here. Now we want to find the maximum, so I need to first figure out what any critical points are. So I'm going to set this equal to 0, and I'm going to get negative 2x equals negative 2, or rather 2x equals 2, x equals 1. So that's our critical point, and now we just need to make sure that that's a maximum, because it very well could not be. So from negative infinity up to 1, and from 1 up to infinity. I suppose I could just take the second derivative of this, but I'm going to go the I'm going to use the first derivative test rather than the second derivative. So let's plug in 0, because that's on this interval. So plug in a 0, and I just get 2, which is positive, so we're increasing on this interval. Increasing all the way up to x equals 1. And then from here I'll plug in maybe a 2. So I get 2 minus 2 times 2, so it's 2 minus 4, or negative 2, which is negative. So we're decreasing. Okay, so x equals 1 is the point of maximum profit. So remember, that's the amount that's being sold. So now we have to plug in x equals 1 to our actual profit formula to figure out what the max profit is. So P of 1 is 4 times 1, which is 4, minus the cost of 1. Well, C of 1 is going to be 0, because 1 minus 1 is 0, so it's 0 squared, which is 0, plus 15. So our profit, plug that back in, it's going to be 4 minus 15, which is negative $11, which means that this is not a very profitable business because their maximum profit is negative $11. So the most money they can make is losing money. That's unfortunate. But that is our answer for this. I hope that makes sense. Let's jump to our next one. Number 3 says the product of two numbers is 63. Find the sum of the two numbers, s of x, as a function of one of the numbers x. Okay, so I'm going to say that that these two numbers are x and y. Okay, so we've got x and y. So I know that x times y equals 63, because that's the first line they told me. The product of these two numbers is 63. Okay, now I want my function to be in terms of x, so I'm first going to figure out what y equals in terms of x. Y equals, well, 63 divided by x. Okay, well, if I want the sum of them, that's going to be whatever x plus y is, and I can now substitute this in for y, so it's x plus 63 divided by x is my sum. It's all that they want there. And now we want to find the positive numbers that minimize the sum. So now we need to find a relative minimum. So we first take the derivative of this. I note the derivative of x is just 1, and the derivative of 1 over x, if I take the derivative of that, is going to be negative 1 over x squared. So it's just this times the constant coefficient. So it becomes the following. And I want to know when that equals 0. Okay, so I've got 1 minus 63 over x squared equals 0. First thing I'm going to do is I'm going to add this to both sides, or I could just subtract this and then the negatives cancel out. But so I'm going to get 1 equals positive 63 divided by x squared, and now I can multiply both sides by x squared to undo that division there. So now I get x squared times 1, or just x squared, equals 63. X equals plus or minus the square root of 63. Now I want to find the positive numbers that minimize the sum, so it's just going to be a positive square root of 63. But they do want two numbers here. So for a moment when I was doing the homework, I was very confused as to what they wanted here. Because if they only want positive numbers and there's only one, or there are two critical numbers and one of them is negative, what can we do? Well, in this particular case, the square root of 63 is one of them that minimizes the sum. And I know the product of the two numbers is 63. So if I had square root of 63 times the square root of 63, that would equal 63. They're both the square root of 63. And I know that feels a little weird. I didn't expect that to be accepted, but that is at least what they were looking for with mine. And it really caught me off guard. Now we want to let C be the smaller of the two numbers and minimize the sum. In this case, it doesn't really matter because they are the same. But if you do have two different ones, then use that one. So c equals this. We know that the derivative of our function, when we plug that in, is going to equal 0 because that's how we found this number in the first place, right? But you can always just go plug that back in, double check. And then we want to find what the second derivative of this is when we plug in that c value. So remember our derivative was this. So now I have to take the derivative again. Well, I know my 1 is going to disappear, and the derivative of negative 1 over x squared, or I guess just 1 over x squared, really, it doesn't really matter though, is going to be those power rules. So that's an x to the negative 2. So I'm going to bring my negative 2 out, negative 2 over, and then I'm subtracting from that exponent, so it becomes a negative 3. And it looks like that. Remember, we're multiplying it by negative 63, so it's turned positive. 63 times 2 is 126. There's our derivative. So now I just have to plug in the square root of 63. And for right now, I will just leave it in those terms. So it's going to be 126 over cubed square root of 63. That's what I'm looking for there. Number 4 is just another derivative and second derivative question using quotient rule. So remember, quotient rule is that low d high minus high d low over low low. So derivative is going to be that low term, so it's x cubed, times the derivative of our high term is going to be 2x minus the high term times the derivative of our low, which is going to be 3x squared, all over low low. And I know x cubed squared is going to be x to the 6th. And now I'm going to multiply those out, right, because we see we can do some distributing there. So it's going to be 2x to the 4th minus 3x to the 4th plus 48x squared all over x to the 6th. Combine like terms, that's going to be negative x to the 4th plus 48x squared instead. So now I see I can factor out an x squared from all of that, so I'm gonna over x to the 6th, and that cancels out a little bit, so now I get this here, and that's our first derivative. So we see our a value is going to be that negative 1, our b value is a 48, and our c value is a 4. And now we just do it again. So again, that low d high minus high d low over low low. So our low term, x to the 4th, times the derivative of our high term, which is going to be negative 2x, minus the high term, times the derivative of our low term, over low low. Again, go ahead and distribute that out. So I'm going to get a negative 2x to the 5th plus 4x to the 5th minus, I think that's 192 x to the 3rd. I think 48 times 4 is 192. And then all over x to the 8th, combine like terms. This turns into a 2x to the 5th. Well, I see that these turn into a 2x to the 5th. And that's all that there. And I see I can factor out an x cubed. So I'm going to do that. And then, of course, my x cubed cancels, and I get this. So now our d is 2, e is a negative 192, and f is 5. This next one's a trickier one. This took me a little bit of time on the homework. It said a crate open at the top has vertical sides, a square bottom, and a volume of 392 cubic meters. Write the surface area S as a function of x. And I'm suddenly forgetting what the surface area formula for a rectangular prism is. So give me one moment. Okay, so the surface area for the typical rectangular prism is 2 times the width times the length plus the height times the length plus the height times the width. But what's important to notice here is two things. First, it's an open topped box, and second, it has a square bottom. So x equals y, and I'm actually going to say that x equals our length, y is our width, and z is our height, right? I know that our length and our width in this case are equal because it's a square bottom. So I'm going to go ahead and plug that back into here. So length and width are the same, so it's just length squared plus the height times the length plus the height times the length again, because those are equal, which makes that 2 times the length squared plus this here, or just this is the surface area, except again, it is an open topped box. We have to take off the area of that top that is not there. So of course, that's just going to be the area of a square, because it's going to be the same area as the bottom, because it's the top, and they're parallel. So we're going to subtract an L squared, I believe, because that is that top bit there. So if I subtract that, I end up with just L squared plus 4 times the height times the length. And so this is going to be our surface area equation. And again, x is L here, so I'm just going to write the same thing over here, except with x's instead of l's. Oh, it says a function of x, and I forgot that our height is not x. That's the tricky bit, yep. Let's see, I believe volume is the derivative of surface area. So volume, but we don't need that. Volume is also just the width times the height times the length, or in this case, just the length squared times the height. Okay. And the volume is 392. So I'm going to take the h and turn it in and put it in terms of our L there. Or I guess I should be using x technically. But yeah, so I'm actually going to divide by our L. So now h equals 392 divided by that. So I can plug that up into there. So our surface area equation is this. So it's 4 times 392 times L over L squared. And of course, one of those L's cancels, and I don't know what 392 times 4 is. I know 300 times 4 is 1200. 90 times 4 is 360, and 2 times 4 is 8. 15, 16, okay. So now our surface area is L squared plus this, because remember, one of these L's cancels. And again, rewrite the same thing just with x's instead of l's. So it's x squared plus 1568 over x. And that's our surface area equation for this open-topped box. Now I'm going to go ahead and erase this work over here for now, if it'll let me. Okay, and now it says if the crate has the least possible surface area, find its dimensions. Well, if our surface area is this function here, in order to find the least possible area, the least possible surface area, we have to find a relative minimum. So we have to take the derivative here. I know the derivative of x squared is 2x, and again, this is an x to the negative first, so I'm going to go ahead and, oops, oh, it won't undo. Ah, why is it freezing now? Oops. Okay. Oh, goodness. Goodness, I did not want that to happen. Oh, and it took away my x from there. Okay, so for our surface area equation is as follows. We're going to go ahead and take the derivative. Derivative of x squared is 2x. And I know it's going to be negative because the power rule there. To x squared. Remember that this is just x to the negative first, right there. So I'm just taking that derivative. And now I just need to see whenever this equals 0. So 2x minus 1568 over x squared equals 0. Well, 2x equals 1568 over x squared. I can multiply by x squared on both sides. So I get 2x cubed equals this. X cubed equals whatever half of that is. It's going to be 500, 250, 34, 784. So I know my x is going to be whatever the cube root of 784 is. I'm just going to see what that is with a calculator. I'm not sure that that comes out to be a pretty number, so we'll find out. Oh, and it does. That is 28. So x is 28. And we know, again, since it has a square bottom, our y is the same as our x. So that's also going to be 28. I know volume is... Oh, never mind. Sorry. I took the square root instead of the cube root. So that's not going to be 28. That's going to be a smaller number. That is a less pretty number, because that comes out to be about this. Okay, but again, that's going to be the same number for our x and our y, and I'm going to go ahead and round that here, but you should not round on the homework. And then if I multiply that together, and then if I multiply those together, it's going to be x times y times our z equals our volume, right? So I multiply this times itself twice, and I know my volume is 392, so I can just do 392 times this squared is going to equal z, right? Because I'm dividing by that, because x times y is x squared. So 392 divided by that, so our z is approximately this here. Again, I'm rounding. And then we want to know what our second derivative of this x value is. So our second derivative, I know it's going to be 2. And that's probably going to turn into a plus and double that. Because again, just power rule, this is an x to the negative second power. I know I'm adding x cubed on the bottom. 2 times this is going to be 3,126, 36. 36? I need to double check that. I'm not super great at doing mental math. Okay, good, that's right. Okay, so that's our second derivative. And if I go ahead and plug that x value into it, then my second derivative, oops, not of x, but of our cube root of 784 equals, it's going to be 2 plus this over, well, the cube root of 784 cubed, it's just going to be 784. And that's probably going to be 4 times, I think. Yeah. So this is equal to 4, so it's equal to 2 plus 4 equals 6. Oh, you know what? I made a mistake. I totally skipped over even checking if this was a minimum. For all we know, that could be the maximum surface area. Oh, but luckily, our second derivative we just found is positive, so it's greater than 0, which means there is a minimum. That means it's concave upward there. So this is a minimum. We did good. Whoops, though. Be careful about that. I'm going to erase a bunch of this, so we've got plenty of space for our next one. And for this question, it says, at 4 p.m., a truck traveling east at 40 miles per hour passes the same spot as a school bus that arrived at the same spot at 2 p.m. while traveling north at 35 miles per hour. Find the distance d between the truck and the school bus t hours after 2 p.m. Okay, so I'm going to go ahead and kind of draw this out on a, not a grid, I suppose, but a little compass almost. North, south, east, west. We're going to say that this is the spot that they arrived at. And so I know we're going to start at 4 p.m. Our truck gets there, and our truck is, it's heading east at 40 miles per hour. But at 4 p.m. it is at this point. That's where our truck is. Now, at 2 p.m., the school bus was also at this point, but it was heading north at 35 miles per hour. And it's going to be quite a distance up by now because it's going to be 2 hours later. So it's going to be 2 hours, so it's going to be up 7 miles because it's been 2 hours, 35 miles per hour. And we're going to call this 0, 0. Okay. So now, this is a tricky bit. So we first we'll come up with an equation for wherever our truck is at any given point and wherever our school bus is at any given point. We'll start with the school bus because that feels easier. Might not be though. So I'll say our school bus is S. And so I know that wherever they are, whatever distance they've traveled is going to be their velocity. So 35 miles per hour times the t, which is every hour, right? And plus some number b, right? Our intercept with this point. So at 2 p.m., so it's t hours after 2 p.m. So at 2 p.m., t is going to equal 0. At 2 p.m., t equals 0. Well, I know when s of t, I shouldn't just write that as s, it should be s of t. S of t. So I know at 2 p.m., my school bus is at 0, 0, right? So it's going to be 35 times 0 is 0 plus b. That all equals 0 because that's where it is at. Which means that b has to equal 0, right? Because it's 0 plus b equals 0. So our equation for our school bus's distance from the point is just 35t. Okay? Our truck is going to be a little different. So again, it's that speed. The truck was going 40 miles per hour, so 40 times the hours plus b. We know that at 4 p.m., so when t equals 2, I know at this point, and t equals 2, I know that it is at 0, which means that 40 times 2 plus b equals 0. So that's 80 plus b equals 0. B is going to be a negative 80 there, which means the equation for our truck's distance is 40t minus 80, or plus a negative 80. And now, at any given point, let's say, I'm going to erase that 70 miles because it doesn't really matter. Let's say at any distance they are away from each other, that's going to be this diagonal line D, right? Let me erase some of this really quick. Okay. So now d of t squared is going to be s of t squared plus t of t squared. That makes sense. That's our Pythagorean theorem, right? It's going to be whatever this distance is squared times this distance squared. That's going to be this squared. So now I'm just going to plug in what we have. 35t squared is whatever 35 squared is. I don't know that. Let me figure that out. It's going to be this number plus whatever this is squared. Let's see, 40t minus 80 squared. It's going to be 40 times 40. That's going to be 1600 t squared. 40 times negative 80 minus this plus this, I believe. I think that's right. If that's wrong, feel free to correct me, but I think that should be right. So then that goes over here. These are some big numbers. Gonna erase this a little bit. Okay. Now combine like terms. So it's gonna be and obviously our actual distance is going to be the square root of all of this because this is squared. But the fun thing here, so I'm going to go ahead and write that. I'm going to write that in my square root because that is going to be our distance. That's all, square root because it's d of t that we're looking for, not d of t squared. But when we want to find the derivative of all of this, we don't actually have to find it in the square root for our purposes. We can just take the derivative of the square. So derivative of d of t squared is going to be 2d of t, right? And that's going to be 2 times that, which is 5650, I think. 5650 t minus that, and now I just divide by 2. 2825 t minus that. And oops, sorry. So ignore this. This isn't technically correct how I'm writing this. But so this is what we want to set equal to 0 to find our critical points now. You could also just be taking the derivative of this, but that's just a little more complicated with the square root, and I personally don't feel like dealing with it. So I'm going to set this equal to 0. So I get this now. So t equals that. And let's see if that comes out to be a pretty or an ugly number. And it's an ugly number. So that's 1.132743363, and that's going to be hours, right? So if we want to, and it's going to be hours after 2 p.m. is when they're closest together. Oh, again, I didn't check if that was when they're closest together. I didn't check that that's a minimum. So let's do that really quick. So negative infinity up to that point t. Let's plug in a 0. It's a nice easy thing. That's going to be negative, so it's decreasing there. Decreasing, and then we'll plug in a 2. 2 is going to be bigger than that, so it's going to be positive and increasing. Good, so this is at a minimum, which means that they're closest together. Since they're closest together at this point, so let's see, now we multiply that by 60 to figure out how many minutes it is. And so that's going to be an hour and about 7.96 minutes. It says to round down to the nearest minute, so we're just going to say an hour and 7 minutes, even though it's closest to 8, which means it's an hour after 2 p.m., so it's going to be 3:07. Hour after 3 plus 7 minutes. And that's what they're looking for. Let's try what's left. Okay, not too much. So number 7 says write a function that models the distance d from a point on the line y equals 2x plus 5 to the point 0, 0 as a function of x. Okay, well, I'm just going to go ahead and draw out a little visual of this. It's not going to be perfect. Obviously, there's 0, 0 right there. And then I've got 2x plus 5, so that looks something like that. Which means that any distance from this given point is going to be something like that. And I can kind of form a little triangle there. See that? I can form a triangle kind of with the x-axis. And so let's take a look. Let's kind of draw out that triangle. Obviously, this height here is going to be whatever this y value is. So it's going to be y. Over here, this point's just going to be whatever x value is plugged in. And this right here is our 0, 0. There's our distance. So this here is x. This here is y. And then we just use Pythagorean Theorem. Of course, y squared is going to be that 2x plus 5 squared. So 2x plus 5 squared, which is going to be 4x squared plus 20x plus 25, I think. Combine like terms, so d squared equals 5x squared plus 20x plus 25. So then our distance is going to be the square root of this. So I'm going to go ahead and write that over here. Oops. And now again, we don't need to take that square root before taking the derivative. So I am just going to do the same thing I did last time. I know this isn't technically correct how I'm writing this. I'm just not really sure how to write it, so please ignore this. This doesn't make a whole lot of sense. It's going to be 10x plus 20, and then divide by 2, so it's going to be 5x plus 10, set that equal to 0. 5x equals negative 10, x equals negative 2. Okay, now we want to check if that is a minimum or a maximum. So if I plug in to this, maybe if I plug in, let's see, what interval are we on? This, let's plug in a negative 3. So this is going to be negative 30 plus 20 is a negative 10, which is negative. So we're decreasing. And then from negative 2 up to infinity, if I plug in a 0, that's just going to be 20, which is positive. So we're increasing, which makes this a minimum, which means that it is the point where they are closest. So it's going to be negative 2, comma, oh, what is the y value? Well, y equals 2 times negative 2 plus 5, so it's going to be negative 4 plus 5, which is 1. That's it. Let's take a look. Now, number 8, this one is a little confusing without that little visual there. And even with it, it might still be a little confusing. Says a forest ranger is 4 miles from a straight road. Right, he's 4 miles away from there. A car is located C miles down the road. The forest ranger can walk 2 miles per hour in the forest and 5 miles per hour along the road. Write the total time, t, for the ranger to get to the car as a function of x, using c for the distance from the end of the road to the car. Okay, well first I need to figure out how far he's going here. Well, this is a right triangle, so I know that this distance is going to be the square of this plus the square of this, and it's just square root all of that, right? So I'm going to say that that's a d, so d squared equals x squared plus 4 squared. So that distance, or I suppose distance 1 is what I'll call it, and this is going to be distance 2. So distance 1 is in the square root of that. And then distance 2 is just going to be this over here, so it's going to be c minus x, right? Now I've got both of these distances, so now I just need to figure out how long it takes him to travel those distances. So if he goes 2 miles per hour on distance 1, the time it takes him to travel this distance is going to be this divided by 2 miles per hour. So I'm going to say time 1 is x squared 16 over 2. And like the reason that makes sense obviously is maybe that distance is like 30. Well, if his speed, his velocity is 30 miles per hour, then the time that it takes him is going to be this divided by that speed, right? So it's going to take him 1 hour. Or if maybe that distance was 15, right? You'd think it would take him half an hour, right? And you see that when you do the distance divided by the speed, 15 divided by 30 is 1/2, so it would take him 1/2 of an hour. Just in case that's unclear. I know I have to really like understand those ratios in my head to be able to make sense of this. Next part is the same thing. We've got the second distance divided by how fast he can go that distance, which is 5 miles per hour. And then the total time it takes him is just going to be the sum of these two. So it's the time it takes him to go this way plus the time it takes him to do that, because it's just he has to go that full distance. So t of x is going to be this plus this. So I'm going to write just like this plus that. And then toward what point on the road should the ranger walk to minimize the travel time to the car? And then they give us different c values. So in order to figure this out, we have to, once again, take the derivative of our equation so we can find our local extreme. We have to find a local minimum. So this one's a little tricky to take the derivative of. So this is our function. Okay. And so first we want to take the derivative of this first part here. Well, I know that's the same as this, so I can apply chain and power rule there. So derivative of my outside is going to be 1/2 times the inside to the negative 1/2 times the derivative of the inside. It's going to be a 2x. Now if I write that as a fraction, it's going to be 2x over 2, because of that 1/2. And this is a negative 1/2, so it's on the bottom and it's a square root. I see my 2's cancel, so I'm just going to leave it like that. And then I see that over here it's still divided by 2, so I can put one of those back. So it's going to be x over 2, and that bit right there, right? Now I just need to take the derivative of this bit. Well, c minus x over 5 is the same thing as c over 5 minus x over 5. C is, as far as we know, it's an unknown constant, right? And when we take the derivative of a constant, it turns into 0. So that c actually disappears, and then the derivative of this, derivative of x is 1, so it's going to be that. I'm just going to change that into a minus instead of a plus and negative. And so this is our derivative now. And I know what you might be thinking that, like, what do we do if the c disappears? Because these questions ask about the c value. Well, it apparently just doesn't matter. Yeah, it just doesn't really matter. And you'll kind of see here in a minute. So first we need to find our critical points. So we need to set all of this equal to 0. So this is a little complex, not my favorite. Equals 1/5 multiplied by 2 to get rid of the 2 in the denominator. And I'm actually going to multiply by this whole bit. So times 2 and that radical there. So I get x equals this. No. I'm going to leave the radical over there. Oops. Uh-oh. I did more of that than I meant to. Equals 1/5 multiplied by 2. X over that equals 2/5. And now I can just square everything. And of course, since this is all multiplied, that just turns into an x squared over this equals that. And now I can multiply both sides by that, so I get x squared equals this. And I'm going to multiply both sides by 25. I'm going to move up here so I've got more space. So 25x squared equals, I'm going to just repeat that, 4x squared plus 64. So that becomes a it's a 21. X squared equals 64. X squared equals 64 divided by 21. X equals plus or minus square root of 64 over 21. Okay. And let's say 64 over 21 is a little over 2. I mean, a little over 3. It's a little over 3. It's like just over 3. It's 3 and 1/21. So I know, just so we don't have to use a calculator, I know it's a little over 3, but it's definitely less than 4. Oh, no, sorry. The inside of square root is that. So it's a little over square root of 3, definitely less than that. And I know that that is greater than 1, and that is 2. So I know that the whole thing is less than 2. So it's between 1 and 2. So now we'll take our intervals just to make sure it is a minimum. Obviously, a negative doesn't make sense for the context of this problem because he can't, like this distance can't be negative because that would be way over here and that doesn't make sense. So it's just going to be the positive square root of 64/21. Okay. And since I know that 1 is definitely less than all this, I can plug in a 1 to my derivative, and that'll be on this interval. If I plug in a 1, I get a 1 over 2 times the square root of 17 minus 1/5. Square root of 17 is a little bit bigger than 4, so this would be about 1/8 minus 1/5. It's not 1/8, but it's about 1/8. Because obviously 2 times something a little bigger than 4 is going to be at least that. 1/8 is smaller than 1/5, so that is negative. So we are decreasing here, going down. If I plug in, I'll plug in a 2 now. Get a 2 over, well, those 2's cancel. So that turns into a 1 over 4 plus 16. That's also bigger than 4, a little bit less than 5. Which means that this is going to be bigger because that's closer to 1/4 than it is to 1/5, and 1/4 is bigger than 1/5, so it's going to be positive, so we're increasing, which means we're at a minimum, so it does minimize the travel time, and that is within c equals 10 miles, right, because we know it's less than 2, so x equals that. Now, because c doesn't actually matter for this, I was initially inclined to just say that this is the same answer here, except this is bigger than a 1/4 mile. That would be outside of c. That would be like if c was this 1/4 mile and we're going way over here now. That doesn't make sense, right? So in order to minimize the travel time here, we have to stay within the sort of interval that they've given us. This is kind of a cap off, and it's just going to be a 1/4 mile. We've just got one page left. So for number 9, if f of x equals this, find the relative extreme values for the function and identify the tail behavior. So I'm going to go ahead and take that derivative. I'm going to need to use chain rule here. So derivative of my outside is going to be that power rule, bring my 2 down, of my inside, subtract the power, so it's just 1 now times the derivative of my inside. There's my derivative, and I'm going to just rewrite that like so. Okay, and I can also rewrite that as this, right, because this is a perfect difference of squares. So my derivative equals 0 whenever x equals 0. So equals 0 at x equals 0, x equals -2, or +2. Okay, So those are my critical points here. I'm going to go ahead and take that second derivative because it's not that bad. I'm going to distribute this out for that. So it's going to be 4x cubed minus 16x, which makes that 3 times 4 is 12x squared minus 16. And now for ease, I can factor out a 4, so it's a 3x squared minus 4. Okay. And so let's go ahead and plug in a 0 to this to see which way it is concave, whether I have a minimum or a maximum. Remember, my second derivative is greater than 0. I have a minimum. If it is less than 0, I have a maximum. Right, it's going to be like that. So let's go ahead and plug in that 0 to see where it falls. So I plug in a 0 and I get 4 times negative 4, so that's less than 0. So that is a max. So that's one of our relative maximums, is f of 0. Let's plug in the negative 2 now. So I get 4 times, well, negative 2 squared is 4, so it's going to be 12 minus 4. That's going to be positive or greater than 0, so that is a minimum. And then if I plug in a 2, I'm going to get the same thing, so that is also a minimum. So we get negative 2 and 2, and then we just plug those back into our original function to see what they are. So I'll start with the 0 because that's nice and easy. It's going to be negative 4 squared, which is 16, and there is no thing for these two. Let's try f of negative 2. It's going to be 0, right? Because negative 2 squared is 4. 4 minus 4 is 0. 0 squared is 0. Then doing the same, 2 squared is 4. 4 minus 4 is 0. 0 squared is 0. And now if we take a look, so I've got my interval looking something like this. This is what these look like. And I know since this is a minimum, it's decreasing, increasing, decreasing, increasing, which means it looks like this. So as it goes to positive infinity and negative infinity, this is our tail behavior. So it's going to be this one here. Now for our final question, it says f of x equals negative sine of x plus 1. Okay. And they want to know what f prime of 0 is, so we're going to go ahead and take that derivative. It's going to be negative cosine x plus 1. If I plug in the 0, well, it's going to be cosine of 0 is 1, negative 1 plus 1 is 0. Do the same for that second derivative. Second derivative is going to be, oops, forgot my equal sign. It's going to be sine of x. Sine of x of 0 is also just 0. So we would expect it to be a relative extreme value, no? Except for the fact that that's 0, which tells us that that is inconclusive, really, for the second derivative test. And so if I take a look at my unit circle, right, I've got from 0 all the way to pi, right here. My derivative is going to be, well, let's plug in maybe pi over 2, right? That's going to be 0 plus 1. Any other cosine value, any other like value I have in here, my cosine value is going to be less than 1. So that's going to be positive, so it's going to be greater than 0. And anywhere down here is going to be the same, right? It's always going to be less than 1, so then we add it to 1, and it's always going to be greater than 0, right? Because even if I have, because it's not inclusive of these points, so maybe I plug in my 3 pi over 2, that's a 0 plus a 1, which is just 1. Maybe I plug in, I don't know which one this is, but I know it is, let's see, that's pi over 4, 3 pi over 4, I think that's 5 pi over 4. If I plug that in, I'm going to get my cosine is negative square root of 2 over 2 plus 1. This is less than 1, so it's still going to be greater than 0. No matter where I pick a point in here, that's going to be greater than 0. So if on both of these intervals, no matter where, if it's always greater than 0, then there's no shift anywhere. There is there's no shift at this point, rather. I hope that makes sense. I'm not great at explaining this one, but yeah, that's like saying that's like from negative infinity to infinity. It's just constantly, it's greater than 0, so it's constantly increasing. And if it's increasing forever, there's no relative extreme values, because extreme values are when it changes from that. But that is all of this problem set here, problem set 16. I hope that this video was helpful. I hope that it made sense. And yeah, thank you for watching.